Hello, my name is Gianluca Martena. I'm a PhD candidate at University of Strathclyde, and in today's presentation I will talk about the paper titled Adaptive WDMA Improving the Data Rate of a LiFi Network that I wrote along with Dr. Bian and Professor Harald Haas. I will start off by giving some context on what this paper is about. Then we will explore the concept of wavelength division multiple access and one of its associated challenges. Then I will describe the proposed solution to solve this issue, and finally an application of this solution in a simulation environment when an everyday use case scenario is taken into account. The use case that we are considering here in this work is indoor Internet of Things in densely deployed LiFi networks. LiFi is the network counterpart of optical wireless communication, where a number of optical emitters is able to deliver a network-like experience to multiple users. This context is especially important in two aspects. First, there can be several different kinds of user equipments whose complexity and mobility needs can range from low to high. These can be smartphones, smartwatches, but also various home appliances and machinery pertaining to the concepts of smart home and Industry 4.0. From this, we understand that flexibility is key. The second thing to consider is that we can expect to have a high number both of these devices and LiFi access points. And it is intuitive to realize that as we increase the number of devices and access points, the interference can only increase and is bound to become a major limitation. And this has something to do not only with the ability of establishing a reliable connection itself, but also with the decreased energy efficiency coming from the fact that we will need more power to overcome the interference. And this brings us to the main challenge that we want to tackle in this work, which is interference mitigation. One of the crucial aspects in mitigating the interference is channel separation. The better we can separate the channels, the more efficient our network becomes in terms of interference mitigation. And from an optical standpoint, we can achieve this by using wavelength selectivity at both transmitter and receiver side, so that a number of wavelength selective channels can be used. In this work, we consider our RGBA system, as you can see, that is employing red, green, blue, and amber transmitter and receiver couples. This means that at transmitter side we have 4 individually addressable LEDs, while each user is equipped with 4 receivers, each with a different optical filter, allowing a different wavelength range. The figure shows the relative emission and transmission spectra of each element that we are calling transmitter elements and receiver elements. In this way, we know that when we say red TE, we are talking about the red LED, while with red RE, we mean the specific receiver with the red wavelength selective optical filter on. Now, back to the spectra. We have to note that this is a specific from 10 designing choice, and it is due to the specific components that we are using. We could have chosen other LEDs and optical filters, it doesn't matter, as long as we maintain the right amount of channel separation. So the basic idea is a transmitter that can serve up to 4 users, and each user only has 1 active receiver at all times. In this way, we ensure that the interference is kept to a minimum. And as you can see, user 1 only has the blue receiver active while being served with the blue transmitter. Same goes for user 2 with the green, and so on. And this is what we call classic WDMA or state-of-the-art WDMA, in which each user is allocated a transmitter-receiver couple of the same color. In order to investigate what we can achieve with classic WDMA in this setting, we have created custom code to run a simulation and evaluate what is the coverage in a room equipped with 25 RGBA LEDs. The room is 10 meters by 10 meters and 3 meters of height. And what happens is that the 4 users we considered before are put all in the same position, with the receivers pointing upwards, and they will move across the room, sweeping every available position. This will help us evaluate what the coverage is in terms of achievable data rate. Additionally, they will also measure the connection loss, which we define here as the probability that the SINR is under a certain threshold, chosen as -6 dB, thus making it impossible to establish a reliable connection. Therefore, a connection loss of 0% means that the user is always able to establish a reliable connection. And this is what we obtained after running the simulation. Each of these 4 squares represents the achievable data rate for each one of the 4 users. The modulation scheme is on-off keying. In terms of coverage, we can very easily notice a big difference among them. However, from a simulation standpoint, the only real difference is the channel that each user is allocated, which is fixed, as we saw before, with user 1 with the blue, users 2 with the green, and so on. And thus, we have to conclude that these are only due to the specific front-end design. This also translates in the achievable data rate that we find having a mean of around 106 megabits per second, but also a very wide spread, ranging from 77 to 128 megabits per second. And however, this is not even the entire story, because there is another crucial aspect that we haven't yet considered so far. And I'm talking about the passband shift phenomenon. It is a very well-known effect that occurs when we change the angle of incidence of a light beam with respect of a surface. If this surface is a thin film optical filter, much like the ones that are employed here, it is possible to observe a shift in the wavelength passband characteristics. And we can see in this animation that as the user moves further and further away to the right, the optical filter's transmission spectra change dramatically. The figure on the right shows the average received electrical power versus the angle of incidence. It is averaged across all 4 users. We can see how there is a small peak at around 10 degrees. This is again because of the front-end design, because the red optical filter spectrum is achieving a better overlap with the red LED spectrum around that value. Otherwise, the curve is generally decreasing, and it can be seen that at around 40 degrees of incidence angle, almost all signal power is lost. So we have repeated the simulation while taking this unwanted but present effect into account, and the result is presented in this slide. As it can be expected, the performances suffer from this effect as the data rates are generally lower, due to the fact that with the passband shifting, the spectral overlaps are not good anymore. Most notably though, the user 4, who is allocated the red transmitter and receiver, has a better data rate coverage in this case. And this is again because of the red optical filter passband being optimized for use at around 15 degrees of angle of incidence. Also, the average achievable data rate is around 95 megabits per second, but is again very spread between 68 and 124 megabits per second. Another thing that can be noted is that the connection loss is not 0 anymore. This is because of the passband shift phenomenon. Then we asked ourselves, is there a way to contrast this effect? Can we somehow modify the channel allocation so that if the orientation of the device makes it difficult to collect the signal with one receiver, switch to another receiver that is in a more favorable situation? And the result is what we called adaptive WDMA. The differences with classic WDMA are 2. First, we leave behind the concept of color. For example, a user would be free to enjoy its green receiver element to collect the signal from the blue transmitter element, while normally it would be bound to select the blue receiver element. This enables to have much higher flexibility. And this is the first difference. The second difference is that in place of assigning the transmitters in a fixed way, we seek to maximize the aggregate SINR while assigning them instead. That means, assuming CSI information is available, among all possible TE, user, and RE combinations, the best assignation is selected and applied in terms of SINR. By doing all this, we ensure that when the angle of incidence of the light is different than 0, putting the user in a potentially faulty situation, we can switch to a different transmitter and receiver combination that can guarantee a better performance. In other words, we can take advantage of an unwanted phenomenon to use the differences between the user's positions and orientations to improve the channel separation in a multi-user scenario. Then we have run the simulation again with this new scheme while keeping all other parameters equal. And these are the results of the simulation. Compared to the classic scheme, it's noticeable that the coverage seems to have a random component. This is because in this situation, where all users have the exact same position and orientation at all times, there is not much point in assigning a specific transmitter element to one user over another, because they all have the exact same options. What we can also notice, though, is that the added flexibility in terms of choosing which receiver element to use is bringing benefits. In fact, the coverage also appears more consistent among users. The connection loss is much lower and the data rate is a lot more robust, even though 4 megabits per second lower on average. Then we can make another small step forward and ask ourselves what this solution would achieve if it was exploited in an everyday use case, when the users are not bound to have the same position and orientation. And in order to evaluate this, we have considered the results from prior studies, and especially the one that I am referencing here, that shows how in everyday use case, the position and orientation of the devices can be described in terms of two random variables. According to their findings that I am reporting here, the position in a room is well approximated with a uniform distribution, while the orientation follows a Gaussian distribution with a mean of 30 degrees and a standard deviation of 9 degrees. Then, we have run another simulation in which, rather than sweeping all possible positions with the receivers pointing up, the users are actually assuming a random position and orientation according to these distributions. This is iteration-based, and in every independent iteration, each user has a different position and orientation. We have run a total of 20,000 iterations, half with classic WDMA and the other half with adaptive, to be able to compare the performances. And these are the results. In the left-hand side figure, there is a comparison between the two schemes for each user. The CDF resulting from the use of classic WDMA is represented with dotted lines, while the adaptive is represented with continuous lines. I would also like to note that while the color of the lines in the graphs are matching the assigned channel in the case of classic WDMA, this is not necessarily the case for adaptive WDMA, since the channel is assigned based on the orientation. The CDFs show that in this setting, classic WDMA is not a viable choice because of the very high connection loss and lower data rate, both on average and per user. On the other hand, we can see how adaptive WDMA keeps connection loss to a minimum, and most notably, the data rate is higher and has a very narrow spread. This suggests that it is a good choice in this setting because the added flexibility enables the network to combine the effects of the passband shift phenomenon and the differences in position and orientation between users and use them to improve its performances. Now, before ending the talk, I'd like to summarize a few takeaways that I think are important. First is that in the device diversity we have in IoT, we need flexibility, especially in accounting for mobility and simplicity. Second is that with wavelength division and optical filters in general, the passband shift can be a hindrance, but potentially also transformed into a resource. And third, that the adaptive WDMA can do exactly that, but it needs to also harness the position and orientation diversity between the users to fully reap its benefits. Thank you for watching.